Hi, this is MC Shetty for a new episode of my Forge modding tutorials for 1.20. In this tutorial we will go on with the tutorial from last time on the same GitHub. We'll add another block. Let's first show you how it looks. So this is the block. It's a block that you can interact with. So you can play buttons, push buttons. Also you see the one prop integration. We will show that too. It shows what we are focusing. And it has a user interface. So what does this block do? Say you put in iron ore. You say play break block sound. See? Okay, let's see it. Block loot. Now it breaks the block as if this was loot. Melt input. Now it will melt the block. So it can also do all at the same time. But see? Very OP, of course. This is just an example. The spawn thing only works with spawn X, obviously. Let's just spawn one fox. Yeah, so basically that's what this does. So on the wiki, I added this already. And let's go to the GitHub. So I have a tag for episode 2, so you can go back to the episode 2 version while still having the episode 3 here as well. Just wanted to show you that. Now let's talk about the block. We add a new block, processor block. This is a bit more complicated. Let's start with explaining properties. So as you could see in the demo, our block has 4 buttons and it also has an orientation. So that means we need 4 Boolean properties for the 4 buttons. And we also need facing, which is a standard property. If you go to it, it's actually one of these values, the 6 directions. So in create block state definition, we add these 5 properties. So there are 6 values for these, 2, 2, 2, and 2. So basically, that's 96 possible combinations. So our block will have 96 different block states. Sounds like much, but actually pretty okay. We also override this method, and this defines the default state when the block is placed. So we want to disable all the 4 buttons. And facing, we want at the get nearest looking direction the opposite. So that means that when you place it, it will place so that the front panel is facing the player. Our block also has a special shape. I forgot to show you that in the demo. Let's do that in a moment. So basically, the shape depends on the direction that it's orientated. And since our block goes 2 pixels, every block is 16 texture spaces. So we make it smaller. The shape is a bit smaller than usual. By the way, we also use no occlusion to make sure that our block doesn't hide other blocks. But that's actually, if you use a shape that's not a full block, then you don't actually need that, but it's okay to have it anyway. Yeah, let's show what I forgot to show in a moment. So first, if you place the block like that, it faces upwards. What are you doing? Okay, you can also place it like this, and this will face the player. Also note how the black outline exactly fits this block. In principle, I could have done it that this was also included, because the shape can actually be multiple blocks, but that's a bit complicated and we'll not do this for this tutorial. One thing though, if you decide to do a more complex shape, make sure you don't do the calculations for that in here, because this must be really fast. It's called a lot. So you should pre-calculate all the possible states and combinations. In our case, that means you should pre-calculate 96 different voxel shapes and return the correct one here. We are using a static model, JSON, for our block. So let's change the data generation for it. So with these, we had these before. We add a new register processor. This is a bit more complicated. Basically, we have a base model, which uses cube as the existing parent, and then we add a new box from 0, 0, 0 to 16, 14, 16. So the top block, the top of our block is where it's cut off, where it's a bit less high. So that's 2 pixels below the max height. And for all faces, we want to use this texture, which is assigned to this texture here. We also define a particle texture, which is the same. That's the particle texture is the one that's being used when you break the block. And we use solid render type. That means that we don't have any translucent or transparent parts in our textures. It's all solid. After making the base, we add the model for the processor itself. So we basically have 8 child models for all 4 buttons, an off and an on variation. So you see each of these buttons has its own coordinate quadrant on the front face of our block. Then we make a multi-part builder, because our block is made out of multiple parts. The first part being the base model that we made here, and then all of those children. So for every direction, we calculate the angle offset and the rotation. So these are calculated in multiples of 90, depending on the direction. Then we add the frame, dus the base model, with that rotation, with that condition, and we also add all 8 possible button models for that same rotation with the same condition. So that's how we get 96 different block states. So in your model, you need to cover all different block state variations. Imagine writing that by hand, by the way. And we also, if this model is added when the button is disabled, this model is added when the button is enabled, and so on. Here are the helpers for the buttons, for the button models. Again, an element, and so it's the same principle. Let's see what that looks like if it's generated. So it's processor block. This is the block state. You see it says multi-part now, while in the others it just directly used the model. So apply this model, that's the main frame, with this X rotation when facing is down. And if you go look at the other cases where processor main is used, that's when it's up, and so on. All the other models, like these, are also added conditionally. You can see here every time the conditions that are needed to enable this model. It would have been very tedious to write this by hand. Look at this. So it's very nice that there is data generation. In addition to all this, it also generated a model. First there's the main model, that's this one. And then there are the 8 children, the 8 buttons in the on and off state. We also need to add data generation for the item, but not that's it, that's the wrong one, this one, but that's simply we use processor main here, so that's easy. All right, let's start with the block entity now. So our block entity will also have, you remember from that we have 1 input slot and 6 output slots. So we create separate item handlers for that. This is for the input slots 1, and this is for the output slot, which is 6. And these item handlers are just normal item handlers. They are unrestricted. These are the ones we use in the code itself. And here, these 3 are the capabilities. For example, we have this one, which is a combined item handler for input and output together. That's when no site is selected, so you get to see all the items. This is the input handler. So while there are no restrictions here, because we want to use it in our block entity, we adapt it here so that you cannot extract from it. That's to make sure that the hopper cannot extract from the input. From the output, we do the same. We also adapt the output items, but we make sure nothing can insert it. So this is how you can make sure that the extraction and insertion is correct. Here in get capability, we get the correct item handler. If no site is specified, we get the generic one, which has all the items. Otherwise, if the direction is down, we get the output, and otherwise the input. When we save our item, our block, that's done here, we need to save both separately, like this. Here's create item handler. The only thing we do here is make sure that set changes is called on the block entity, like we did in the previous tutorial. And then we also have our adapted item handler, which is just very simple. It's an item handler that itself takes another item handler and just delegates everything. It doesn't do anything else, and by doing that you can use it like here, where you override specific methods. We also need, of course, to do the registration. So these 3, the block, the item, and the block entity, are the same as with the others. This is new, we covered that in a moment, and we also added to Creative tab. Let's now talk about the user interface. So on the client side, user interface is made up with a screen. So we have processor screen, and it extends abstract container screen with a container. I will explain container in a moment. We have a background that we want to use, which we defined here. Just a normal regular background. This is where the inventory label will appear. We have to adjust that, otherwise it will appear at the wrong spot. And then you override render background. You get a graphics object. Partial ticks. Partial ticks, I need to explain, it's not important here, but partial ticks, so you know that Minecraft, there are 20 ticks per second, but rendering is faster. Usually you have frame rate of 60 FPS or even higher in some cases. And partial ticks indicates how far you are between 2 Minecraft ticks. So for animation that can be important, but we don't use that here. But basically what we do here is we just render our processor texture or user interface texture in the center of the screen, and we use the entire texture. That's done here. So that's all there is to it. That's very easy. It doesn't actually seem to show any items because that's not happening here. The container is responsible for that. Let's show the container. So while the screen is client side, the container is both client and server side. When a user interface is opened in Minecraft, it starts on the server. I will show you in a moment how that works. The server will open a container, and this will cause Minecraft to send a signal to the client that a container has to be opened there as well, and also an associated screen. So the container contains information about all the slots, item slots that there are. In our case, we have a slot for the input items, and we have 6 slots for the output items. With every time we have a coordinate on that user space, or these coordinates for each of these. And we also need to add the slots for the player inventory. So basically we show slots from three different sources. That's how this works. In a container you also have to implement this one. That's the method that makes sure that when you shift click on an item, it will move to a usable spot. So slot count, let's look at that. That's equal to 7, 1 plus 6. And if index is less than slot count, that means that we hit one of our input or output slots, and then we try to move it to the rest of the inventory somewhere if there's place. So if index is not smaller than this, then we try to move it to the input slot if possible. If that fails, we try to move it between the hotbar and the rest of the inventory. That's normal vanilla behavior. We also need to override still valid. That's to make sure that the player isn't too far away from the block to have the screen open. So by adding slots to the container, the synchronization between the server and the client is handled. It's automatic, you don't need to do anything. Containers can also synchronize 16-bit integers. That's using at data slot, for example. And then you can do something like this, get and set. And this is called on the client side, and this on the server side. And this way you can communicate, for example, for a furnace, how much progress there is. But we don't do this in this tutorial. Keep in mind though that although it says int here, you can only do 16 bits due to networking. Speaking of networking, it's the container. Minecraft uses networking to handle the container communication. You don't have to do that on your own. We also need to register the container. That's done here. It's on the menu types registry, which we also have to add right here. This is a bit more complicated, so we register a container. We use this convenience method, which takes a lambda that gets a window ID, a player inventory, and a network packet data. And by convention, this data packet will contain the position of the block that was right-clicked. I will show you how that gets there. So this is called client side, and it will create the container window on the client, the processor container, I mean. You also need to register the screen, and that happens here. Basically in init FML client setup event, you need to do this. So you get the container and you associate it with the constructor that makes the screen. Very important, you have to do it like this to make sure that it happens on the main thread, because init itself can be called on another thread. And you can't do this kind of thing on that thread. So now let's see how we actually open the user interface. We do that by overriding use in the processor block. And we open the user interface on the server. So if not level is client side, then we get our block entity. We check that it's correct. Normally it should be, but it's safer to do that because due to desyncs and so on, it could possibly be wrong. We make a container provider where we again make our container. So this is the place where the container is created on the server side, while this is the place where the container is created on the client side. And on the server side, we know our position, so we can just give that directly because it's given to the use method. And then we open the screen. This is a convenience method. We give it a player, we give it a container provider, the menu provider, and we give the block pos of our block entity. And this will be given to the network packet that is responsible for opening the container on the client side. And that's how this data will get the block position. So that's how it works. So that's what you need to do to open a user interface. Let's cover the rest of the datagen. We'll already, you need to add the processor to the mineable with pickaxe and needs iron ores. Also language for the processor, also for the screen title, and we also use, I will go over that in a moment, for actions. We haven't covered the processing itself yet. We also had the recipe in the processor, and this here we have to change something, because as you remember, our processor has two inventories. We have two tags, input and output. We also need here, we also need to copy these two tags in our loot table because we want to remember the contents when we break the block. That's why we extended this method with an array of tags, and for each tag we add a copy NBT function. And you see here for our complex block from the previous tutorial, we changed that to this, just that tag. And for our processor, we have two tags that we need to save. So that's how we fix that. Finally, let's talk about the actual functionality. Not finally, there's something else after that, but let's now talk about the functionality. So what we want to do is, whenever the player hits one of the buttons, we want to notify this to our block entity. The problem is, in processor block, there is an attack method. This is called whenever the player left clicks on a block in survival. However, it doesn't give a position where on the block the player clicked, and we need that because we need to know which button was clicked. So we can't use attack. Luckily, Forge has an event, player interact event LeftClickBlock. So we add a new class, Forge event handlers, and we subscribe that to the Forge event bus here. in our constructor. This event is fired whenever the player interacts, left clicks on the block. The first thing that we need to do is check if it's our block, otherwise we do nothing. So that's what happens here. We check from the block state what direction the block is facing, and if that direction is the same as the face that the player clicked on, then we cancel the operation. This is to make sure that when you hit with left click our processor in creative on one of the buttons, the front side, we don't actually break the block like what would happen in creative normally. So that's why we cancel that event. Then we go client side. We check if we are client side, because only on client side can we find out where the block was hit. And here we use something we made of ourselves. So there's this method, Minecraft.getInstanceHitResult. That's the last spot that was hit by the player. However, Minecraft is a client-side class. You can see that if you go here. It's only on the client. So that doesn't exist on a server, so you can't use that in server code. We know that we are not on the server here because we just checked that we are on the client, so that's okay. But we still have to use a separate class, because say that you put this here. This would not work because this class doesn't exist on the server. So this entire function cannot run on the server because there is a missing class. To protect against that, you need to put that in a separate class. So a server can safely have this code, because it will on the server it will never hit this line. So that's okay. So we get the last thing that was hit, and we check if it was a block hit. Inside hit, we find the location where we hit our block, and we subtract the position of our block from that, so that we get a relative location in 3D. And then in block process block, we have a convenience method that, depending on the facing, the side that we hit, and this vector, we calculate which of the 4 buttons that was hit. So that's done with this routine. So first we transform our 3D location to a 2D location, which with this, depending on which face our block is facing, which direction our block is facing, and then we see which part of the block of the face was actually hit. But now we need this information on the server side. So the quadrant that was hit, we send that to the server with a packet. That means we need to do some networking. For that purpose, we added a channel class, where we have simple channel, which is a class that we can use for networking. We register our network channel, and we register our message, our packet. So basically what we have here, we have a decoder, an encoder, a consumer, a main thread, and add. Actually, oh yeah, I may actually not have to do this. I didn't notice. Yeah, I will explain that in a moment. I suppose let's check the communication. Yeah, indeed. I will normally in the handle, we also networking is also a separate thread. That's why I added this code in our handler. But actually we don't need to do that, because apparently it's already on the main thread. Okay, so that's easier. I will commit that in a moment. Okay, so basically decoder tells the networking how to convert a packet, which is a byte buffer, to our object, while the encoder says how to convert our object to the byte buffer. So this is how, using the encoder and the decoder, is how you serialize the object to something that can be sent over the network. And the direction of this packet is from client to server. So on the server, this will be called on the server. Alright, so this is our packet. We need a position in it because we need to know what block was clicked and which button was clicked. So that's basically it. And when the packet is received on the server, it's sent on the client and it's received on the server, we get our processor at that position and we call hit on it. So now we are in the block entity. This is called server side. Whenever the player hits a button, we get the correct property, which button it is, and we get a message to tell to the player. That's one of these 4 messages, which are translated right here. So we have to toggle the button that was pressed. We get the block state that we are currently having, and we cycle it. Cycle means that it will get a new value. So for a boolean, that means from false to true or from true to false. And this returns in a new state. Remember, block states can't be modified. So whenever, for example, something that's very confusing for people, that you can do set value. For example, this would seem to be the same as cycle, but that actually doesn't do anything because this set value, it's a confusing name. You have to assign it to a new value because new state itself cannot be modified. So that's important. So when we have our new state with the button toggled, we set block and update it so that the client also knows. We get the actual value that it is right now, and depending on that, we display a message to the client right here. We add a parameter to it, so that's the message, and depending on the value, we add off or on. As you can see here, that's red there. And we also play a sound, the standard vanilla stone button click, on or off depending on the value. So that's all that we do in hit. So what happens now? In our tick server, which is here, 2 times per second, we check the value of all our 4 buttons by getting it from the block state. And if one of them is selected, at least one of them is selected, we extract the item from the input. If that's not empty, we process that item multiple times if needed, depending on which button is selected. So for example, button 0, we melt the item. Button 1, we break it as a block and get a loot. Button 2, we play sound from that block. Button 3, we spawn them up. And the result of this operation is inserted in the output, or if the output is full, ejected. So here we try to insert it in output items, and if that fails, we make a new entity, an entity item or item entity, and we place it slightly above our block where we spawn it in the world. So that's an example of what I showed in the first tutorial of an entity that contains an item stack. So the item stack is given right here. So the 4 operations then, there's melt item. We create a simple container for our input. We get a recipe manager for smelting. And we If there is a recipe, we assemble it, and or else we return empty. So this will return the result of melting that stack. Break block, similar. If our stack item is instance of block item, that means that it actually represents a block. You can actually do it like that. That's cleaner. And then we can get the blocks from it as if we would use a diamond pickaxe. So basically what we do here is we make a loot params builder and we get the drops from the block contained within the item stack. If that's not empty, we get one random loot from it. Otherwise we return the item itself. Play sound will simply play the break sound that belongs to that block. We also use instance of block item here because normal items don't have sounds. Spawn mob will try to spawn the mob if the item is a spawn egg. Here you see we create we get the entity type from the spawn egg and then we will spawn the mob. It's very easy. So that's how the processing actually works. I think we covered everything from the block entity. Yeah, okay. Now the very last thing of this tutorial, we also want to actually have integration with the one probe. In the first tutorial, we already added one probe as a dependency right here. So we already have it in our development environment. What we do now is we add a top compatibility class, and if you want your mod to work without the one probe present, you cannot use any of the one probe API inside your mod itself. You always have to do it through a wrapper, and this is that wrapper. So this class ensures that it's safe to use the one probe without having the one probe in your mod or present in your Minecraft mod pack. So if the one probe is not loaded, we just return here in the register call, and register is called from here in comment setup. Otherwise we use inter-mod communications, EMC. So that's something that you can use to send messages to other mods that support it. And the one probe supports this function and returns the API for the one probe, which is done right here. So you implement a static class, get the one probe, that implements a function which will get as a parameter this API. This is the API for the one probe. And if the one probe is present, this will be handled and apply will be called. We mention on the log that we enabled support for the one probe, and we register on that API a new provider. This provider will be responsible for adding information for our own blocks. So in the add probe info, which is called whenever the player is looking at the block, we first check if it is our block, and if so, we add the extra information that we need. So what do we do here? From data that's given by add probe info, we can get which place on the block was hit. We subtract the position, similar to what we did in the Forge event handlers. We get the quadrant, so we know which button the user is looking at. We have two styles, default style and selected style. And selected style is simply a copy with an other border colors. And then we show the state of the 4 buttons using that style. So for 0, for 1, for 2, for 3, and we show the same translatable action with on or off. So that's all there is to it. Just this one single class is enough to have integration for the one probe. There's a lot more you can do. This is just an example. But yeah, it shows how you can do it. So that concludes this tutorial. It was a bit more complicated, but if you have any questions, feel free to ask. And bye bye, see you next time.